In this video, we will cover inter-domain routing. Border Gateway Protocol (BGP) is a standard that implements inter-domain routing. A quick recap first. Routing helps build forwarding tables at the routers, and we saw two types of routing algorithms: distance vector and link state. Routing in the internet, however, is a lot more complex. We need to handle policy, scale, and performance. What these mean, we will look at them shortly. BGP is a protocol that handles these and is an extremely complex protocol. In fact, to this day, many issues are not very well understood, and there are very few people who possess very good knowledge of this particular protocol. I'm not one of them. I think a prerequisite there is you should work in a tier 1 ISP for many years to be able to know how this protocol works. But this is what holds routing together in the internet. So we need some rough understanding of it. So that's what I'm going to provide, a high level picture of how routing works in the internet. So here is a simplistic view of the internet. In fact, many people hold this view. They think that hosts and servers are plugged into the internet via these routers, and all the routers are the internet are interconnected in this fashion. And you run routing algorithms on these routers and determine paths from the host to the destinations. By the way, this link here could be an extended LAN, but that is a link layer issue. At the network layer, this is how things look. Wish things were so simple, routing would have been a lot less complex. This picture is far from reality. I had mentioned earlier about internet service providers and how organizations take the service from these internet service providers. Within an ISP, there will be many routers, and these routers can serve different organizations, and the ISPs in turn are interconnected in this fashion. This is closer to the reality, but we are not quite there yet, because to achieve connectivity, that is for a host in one ISP to send a packet to a host in another ISP, the ISPs needs to cooperate. But these ISPs are competitors, and cooperation and competition don't go hand in hand. For example, if ISP Y is the competitor of X, X may not want to send traffic via Y. Why? Y can treat its customers well, but the traffic that comes from X, some of the packets it can drop, and thereby the customers of X are going to see degraded performance, and then they may move to ISP Y. Such devious action can very well happen when there is competition. So many ISPs want complex policies like my traffic should not go through some other ISP's domain. So we will see more of these policies later. Not only that, all ISPs are not created equal. So within ISPs, one can categorize them as tier 1, tier 2, tier 3. Tier 1 ISPs are global in scope. In other words, the routers within tier 1 have no default route. What this means is they know how to route traffic to any IP prefix in the internet. Tier 2 ISPs are often statewide or national-wide if the country is small. And they often take the services of tier 1 to reach certain IP prefixes because they don't know how to reach all IP prefixes. And tier 3 are local or regional in scope, which in turn take the services of tier 2 or tier 1 to service their customers. Each ISP itself will have many routers, and when you interconnect ISPs overall, there will be many routers in the internet. So when you handle routing, scalability is a big concern that also needs to be handled effectively. So this is more the reality today. So you have this big tier 1 ISPs which have no default routes. For example, AT&T and Sprint are examples of tier 1 ISP, which provide service to tier 2 ISPs, which in turn provide service to tier 3 ISPs. And these organizations, depending upon how big they are, some of the smaller organizations take service from tier 3, some of the intermediate organizations take service from tier 2, and some of the really big organizations plug in directly into tier 1. Notice also that an organization can take service from multiple ISPs for fault tolerance or load balancing purposes. Similarly, a lower tier ISP can also take the services of multiple higher tier ISPs like here. Before we handle inter-domain routing, we need to understand the relation between the ISPs. Well, let me call this ISPs. Often the relation between ISPs is that of a provider-customer. These relations are also called transit relations. And in these relations, very often there is money involved. For example, the tier 2 ISP will buy service from tier 1 so that the traffic that is originating from its customers, it will route via tier 1 to reach their intended destination because it doesn't know how to reach those destinations. Similarly, tier 3 will also buy service from tier 2 to route its traffic. Sometimes the relation between ISPs could be one of peering, where each ISP provides mutual access to a subset of its routing tables. Often in peering, there is no money involved. So this falls under the paradigm of you scratch my back, I'll scratch yours. So why are such relations formed? For example, let's say the customers of tier 2 have traffic destined to networks that are being served by Y. Now if this peering relation wasn't there, this traffic would have gone to tier 1, which in turn would have sent the traffic to tier 2 to these particular networks. In which case both this X and Y tier 2 ISPs are paying money to tier 1 to do this job. But however, if tier 2 ISP, this Y, told X that if you have traffic corresponding to these networks, you send them to me, and if I have traffic corresponding to your customers, I will send them to you. That way we don't have to spend money paying this tier 1 ISP A. So with this relations as a background, let's see how routing is done in the internet. I had mentioned the term routing domain before. Basically, all the routers that are controlled by a single administrative entity form a routing domain. Another name for routing domain is an autonomous system, AS. We will use both these terms interchangeably. So any network within an organization or a network within an ISP, where by network here I mean a network of routers, forms an autonomous system. So as far as the routing problem is concerned, there are two aspects. One is to solve the routing within an autonomous system, and another is to solve the routing across autonomous systems. Routing within an autonomous system we already saw. This goes by the name intra-domain routing. This routing employs what is called an interior gateway protocol, this IGP, and the examples of this are the OSPF RIP. OSPF does link state, RIP does distance vector. Often the focus on this inter-domain routing or these interior gateway protocols is finding optimal paths within that particular routing domain. And naturally different autonomous systems, because they are distinct, can implement different IGPs. One can implement RIP, another can implement OSPF, so on. However, to route across autonomous systems, you need a different routing protocol. This is called the inter-domain routing protocol, and this employs what is called an exterior gateway protocol. This BGP is one such exterior gateway protocol, and the current version is BGP version 4. Now, this protocol focuses on reachability, policy, and scalability. We are no more concerned with finding optimal paths. In fact, we are more concerned with implementing policy, because these become more important at the autonomous systems level. And when you implement policy, you are more interested that you can reach that particular IP prefix rather than whether I can reach it in the shortest path. And this particular routing protocol has to be common across all the autonomous systems, otherwise it won't be interoperable. We have been talking about these policies a lot. What are these policies? These policies are often dictated by political, security, and economic considerations. When you have various interconnected autonomous systems, each autonomous systems want to implement certain policies. For example, this autonomous system may not want its traffic to go to AS2 because it's its competitors. It would rather prefer this path over this path. Even though if this were the shortest, it will not use it. It wants to go through some other AS. At times, the rule may be that I would like my traffic to go through AS3, but if I am not able to find some path, I may be okay with going to AS2. Such rules may arise where, for example, this is providing cheaper service, whereas this is providing expensive service. So you may want to minimize the amount of traffic you want to send through this other ASP, AS2. Sometimes you may have even such rules. For example, if country X and country Y are at war with each other, you don't want traffic from X country to go through the Y's country routers. You may even have such rules. If Google is buying service from a given ISP, it may specify that whatever traffic that is originating or ending in it cannot go through Facebook domain. This could be for security reasons. Now, how does one implement these policies as part of the routing? That is the challenge, which we will see soon. This is a good time for a break. Don't take too long lest you forget what we have seen so far.